We are a week out from our first exam. That'll be, or our second exam, excuse me, the exam for this unit. That'll be a week from today. Today we're going to cover a topic called a homomorphism. So group homomorphisms is in particular what we're going to cover, and something called a kernel. Both of these objects are really important to the theorems that we're going to discuss Monday and Wednesday of next week. I have tentatively scheduled Monday as your terminology quiz for this module. This would be module 6. We will get through all of the homomorphism and kernel stuff that's on that list today. But the two big theorems that we are not going to cover until Monday and Wednesday, we obviously won't get to. But they're still going to be on that terminology quiz. The two theorems are the the first isomorphism theorem for groups, and the fundamental theorem of finite abelian groups. So there are two things on your list that we will not get to, but you are responsible for knowing the statements of those two theorems. We'll talk about them next week, but I just wanted you to be aware of that. So we have our definition terminology quiz for unit 6 or module 6 coming up on Monday. And then on Wednesday, we have the typical skills quiz, proofwriting assignment due for that module. And I've structured the skills quiz so that you will have covered most of, well, I think pretty much all of what's on there before Wednesday's class. So you should still be good to go on that. The one thing I'll say is there's a lot of stuff to kind of keep straight on this unit. There are a lot of results that we can use to prove different things about groups. And what I'm going to try to do is design a review for the exam that focuses on just all the things that you know in given situations. For example, if you're proving something about a subgroup, here are all the things we know about subgroups. If you're proving normality, here's all the things we know about normality. So I'm going to try to structure the review more as a guide for you to have than as a list of topics. I will include a list of topics on there, but I'm also going to do some other stuff. Expect that to show up this weekend, maybe as soon as this afternoon, depending on if I have some time in the schedule to work on that. So I'd expect to see a review for the exam show up this weekend at some point. Also, I've kind of caught up on your proofwriting assignments. I've graded up through number 4 now. Number 5, which you turned in on Wednesday, I'll grade this weekend. Along with the answer key, so you'll have access to that ready to go for the exam. Do y'all have any questions about the schedule or anything like that leading up to next week's exam, since we're a week out? All right. Well, if there are no questions, let's dive into the topic for today. We're going to be looking at what is called a group homomorphism. So we've already talked about one morphism, actually a couple of morphisms this semester. We've talked about isomorphisms and then sort of subcategories of isomorphisms called automorphisms and interautomorphisms. A homomorphism is a relaxation of the requirements for an isomorphism. So the definition of a group homomorphism is a mapping from a group to another group. And unlike isomorphism, I don't care if the mapping is one-to-one or onto. It can be neither or either. But I do require that it preserves the operation. So all a homomorphism is it's a operation preserving map from one group into another group. The word homomorphism comes from a combination of a Greek word, homo meaning like or similar form, and morphism is talking about the form of things. So like form or similar form, you're going to see why that's an apt description of what we're talking about today. Isomorphisms, which we talked about earlier in the course, are one-to-one and onto homomorphisms. So one of the things I want you to think about as we're going through today is go back to the lecture on isomorphisms and compare the list of properties that isomorphisms have with the list of properties that homomorphisms have. And that will tell you what properties are left out when you leave off one-to-one and onto as potential properties for isomorphisms. So if you relax the condition that the morphism has to be one-to-one and onto, what properties do you give up by doing so? We're going to address that a little bit today. It's also addressed in the videos that I've linked, but it's an important thing to kind of think about. Finally, probably the most important definition here is this one at the bottom, and that is the definition of the kernel of a homomorphism. So the kernel of a homomorphism from a group G to a group G bar, if you will, but the identity of this group that it's mapping to is E, is the set of all elements in the domain that map to the identity in the range. So it's the set of all elements that map to the identity. This is the single most important definition for this next week, because most of the results that we're going to look at together rely on us understanding what a kernel is and the effect it has on a homomorphism, or in some cases an isomorphism. For those of you that do have a linear algebra background, the thing that we're talking about here is something quite interesting. A homomorphism is nothing more than a linear transformation. So from a linear algebra course, any linear transformation that you make is a homomorphism. They are the same thing. It's if you treat the space R2, for example, as a group, right? We can look at, the direct product of R with R and treat it as a group. A linear transformation is nothing more than a group homomorphism from R squared back into R squared. So it's kind of like a group automorphism, homo-automorphism. The null space of a linear transformation are all the things that get mapped to zero, to the zero vector. Well, those things are in fact the kernel of that transformation. So when we talk about the null space in linear algebra, what we're really talking about is the kernel of the group homomorphism that represents the linear transformation. And then if you can actually invert the linear transformation, so thinking about invertible matrices, those are actually isomorphisms, not homomorphisms, because we'll see that there are certain linear transformations that can't be inverted. Those are what we're categorizing as homomorphisms today, because they're mappings that I can't invert. So those of you that have had a linear algebra background and have taken the course, I want you to understand that these topics we're talking about are things that we're going to talk about more deeply in the second semester of this course, and they relate directly to some of the things that you've seen in linear algebra. All right, so let's look at some examples of homomorphisms. This will give you an idea of kind of what's going on. Then I'll ask you some questions in learning catalytics. So the first example that I want to discuss here is we have a mapping from the set of, this is invertible 2x2 matrices. So the set of invertible 2x2 matrices onto the reals minus 0. So the real numbers throw away 0, the punctured real plane, or the punctured real line. We're going to associate a matrix with its determinant. So we're going to map every matrix in the space of invertible matrices to its determinant. And I want to know, is the determinant map a homomorphism? Well, the only thing a homomorphism has to satisfy is operation preservation. So all I have to really ask here is phi of A times B, well, that's the determinant of a matrix A times a matrix B. But we know from linear algebra that the determinant can be distributed across products. So that's the same thing as the determinant of A times the determinant of B, which then would be phi of A times phi of B. So the determinant map is indeed a homomorphism. What is the kernel of that homomorphism? So the kernel of the mapping is the set of all matrices, all 2x2 matrices, such that the mapping, which is the determinant map, sends those determinants to 1. And the reason why it's getting sent to 1 is the identity element of the range group. So the group that's in the range, 1 is its identity element. So the kernel is everything that gets sent to the identity. These are all matrices whose determinants are 1. We've talked about another group this semester that represents that. What group is that? What group consists of all 2x2 matrices with real entries who have determinant 1?
SL2.
Yeah, this is SL2R. So if you use the determinant mapping on the set of the general linear group, which is the set of invertible 2x2 matrices, you get the special linear group, which is the set of 2x2 matrices with determinant 1. That's going to be important going forward. Another example, the group of all polynomials with real coefficients under addition. So G is the set of all real polynomials, all right? They could be any size. So a n x to the n, b a n minus 1, x to the n minus 1, a 2x squared, a1x, a0, such that all of the ai's are real. That's our group. It's the set of all polynomials with real coefficients, and the operation I'm going to use is addition. So I'm adding the polynomials together. Is the derivative that we know from calculus, is the derivative map a homomorphism? So let's think, what would the derivative map look like here? So the elements of G are functions, right? They're polynomials. So if I define phi from G back into G, and the reason I'm defining it from G back into G is if you take the derivative of a polynomial, you get a polynomial back, right? So this will be a mapping from G back onto itself, defined by phi of f of x is f prime of x. Now I have to ask, is that a homomorphism? Well, consider if I had two polynomials added together, the derivative map would take the derivative of these, but we know the derivative distributes across addition, so it would be the derivative of each of these, but that's just phi of f and phi of g. So the derivative is itself a homomorphism from the group of polynomials back into the group of polynomials. Question here is, what is the kernel? Does anybody know what the kernel is? Kernel would be everything that gets mapped to whatever the identity is for this group. So what's the identity for this group?
0.
0. And as Wyatt put in chat, what functions do we know mathematically have derivatives of 0? Constants, right? So the kernel here is the set of all constant polynomials. So the kernel of the derivative map on the set of polynomials is the set of constant polynomials, because they would all get mapped to 0. All right, our final kind of example, just to get you kind of familiar with the concept. I'm going to define a mapping from the integers into the integers mod n by doing the mod n operation. So we're basically asking, is the mod n operation that we're used to, is that a homomorphism? And if so, what is the kernel of that homomorphism? So we'll start with asking, is it a homomorphism? Take two integers, a and b, add them together. Because remember, this is an additive group. Both of these are additive groups. So phi of a plus b would be a plus b mod n, which we know from experience is a mod n plus b mod n, which we know would be phi of a plus phi of b. So it is a homomorphism. It preserves the operation. What is the kernel? Well, the kernel would be the set of all elements in the integers that get mapped to 0. So it would be the set of all a and z such that phi of a is equal to z, or z is equal to 0 mod n. So what's another way to describe this set, given the notation we've used this semester? Set of all integers that are equivalent to 0 mod n.
The set of all integer multiples of n.
Set of all integer multiples of n. Okay, we had another notation for that, because the kernel is going to live in the integers. Yeah, I'm talking about the cyclic subgroup generated by n. Right, so the cyclic subgroup generated by n is the set of all multiples of n in the integers. So the kernel of the mod mapping is the cyclic subgroup of the mod. And that will also be an important result to remember coming up here really soon. So hopefully we're getting an appreciation for what the structure is of these homomorphisms. We're going to look at some properties here in a second, but I want to give you a couple to try as well. So the first one that I want you to weigh in on, if I try to define a homomorphism from the set of permutations on n elements, so this is the symmetric group Sn, onto Z2, 0 or 1 mod 2, given by I assign the permutation to 1 if it's odd, and I assign the permutation to 0 if it's even, is that a homomorphism? So true, false, yes, no. Is that a homomorphism? And then if so, we'll talk about the kernel. All right, I'll give you about 30 more seconds to decide. All right, looks like everyone has answered. And 100% of you are in agreement that it is a homomorphism. How do we prove it? I've got two permutations. Phi of sigma 1 composed with sigma 2. What are the possibilities? Yep. So let's do it this way. This one could be either even or odd. This one can either be even or odd. And what I want you to see is, let me denote it this way, phi 1e composed with phi 2e. That's where they're both even. So if they're both even, what would we get?
Still even.
Still be even. So this would map to 0, right? If we did phi1 odd, phi2, or excuse me, phi1 even, phi2 odd, what would we get?
Something odd, so it would map to 1.
Right, because what you end up having, remember, is if it's odd, it can be written as an odd number of transpositions. If it's even, it can be written as an even number of transpositions. So when you compose them, you're going to get an odd number of transpositions and an even number of transpositions. So an odd plus an even would be odd. So this is going to get mapped to 1. Phi of 2, or phi of 1 odd, composed with phi of 1 or phi of 2 even. Since they're different, they would go to 1. And then this would go to 0. So the question we have to ask is in every case phi of sigma 1 phi of sigma 2 equal to what we have there? So in the first case, you would have even, which is 0, times even, which is 0. This would give 0. Or actually, excuse me, it's plus. Remember, we're doing this mod 2, right, in Z2. So phi of sigma 1, and so I'm following these 4 cases. You have even. Both of these would be 0 if the transposition is even, so 0 plus 0 is 0, it matches. If you had the even and odd case, you would have 0 plus 1, which is 1. Here you would have 1 plus 0, which is 1. And in the both odd case, you'd have 1 plus 1, which mod 2 is 0. So you can see that this maps to the same outputs as this does. Therefore, phi of sigma 1, sigma 2 is the same as phi of sigma 1 composed with phi of sigma 2. So it is a homomorphism. What is the kernel of this homomorphism? It's the set of all sigma in Sn such that what's true? What gets mapped to the identity? Anything that's even. We have another name for that. What is the group that we've studied this semester, which consists of all of the even permutations of Sn?
The alternating set, right?
Yeah, the alternating group An. So it turns out that that alternating group An is the kernel of the parity homomorphism. So if you put a parity homomorphism on the group of permutations of n elements, you get the alternating group for n elements. The even ones get sent to 0. All right. So let's try another one for y'all to make sure that we're on board with this. Suppose I'm mapping z cross z, so coordinate onto z by just taking the difference of the 2 coordinates. So this is a difference map of my 2 coordinates. And I want to know, is this a homomorphism, true or false? And if it is a homomorphism, what type of homomorphism is it? So you can have a homomorphism, an onto homomorphism, a one-to-one homomorphism. You can have a homomorphism that's both one-to-one and onto, which would make it an isomorphism, or it could not be a homomorphism. So when we talk about homomorphisms, there are many possible types, and I want you to tell me which type is this. I'll give you about another 30 seconds. All right, so everyone has answered. The correct answer is B. This is an onto homomorphism. Remember, the term onto means every element in the range gets mapped to. So if I look at, whoops, wrong screen. If I look at, there it is. If I look at this mapping, you know, this is what the range looks like. This is what the domain looks like. Onto means all range elements are hit. So every possible integer is a difference there, which is true, right? I mean, you can create any difference you want, just let A be 0 and then run through all the integers for B, and then let B be 0 and run through all the integers for A, and then you have every possible integer as a difference. So all the integers get hit. It's not one-to-one, however. The reason it's not one-to-one is consider something like AB and A minus B, where AB is like 2, 1 and 5, 4. Both of those get mapped to the same element, which is their difference, which is 1. So remember, if you have two domain elements go to the same range element, it's no longer one-to-one. So it's not one-to-one, but it is onto. And is it clear that this is a homomorphism? Maybe that's not clear. Let's look at it real quick. If I take AB and CD and add them together, because the operation on this set is addition, the operation on this set is addition, that would be, let's see here. I'm mapping a coordinate to its difference. So this will be A minus B plus C minus D. Actually, it's better to explain it this way. So this would be the operation here we know is done component wise. So this would be phi of A plus C, B plus D. Yeah, this is the better way to explain it. This would be phi of A plus C, B plus D, because the operation on Z cross C, or this is the direct product, right? So Z plus Z. So the operation on that external direct product is addition component wise. So this is the same thing as A plus C, B plus D, which according to our definition would be A plus C minus B plus D, which is A minus B plus C minus D, which is phi of the component AB, phi of CD. So it is in fact a homomorphism. What's the kernel? The set of all coordinates A, B, such that A is equal to B. So it's everything that lies on the line y equal x, but only on integer values. All right, I think we're getting the hang of this. Let's do this example together, and then I'll give you another one to think about yourself. So we've got a mapping. It's the square mapping. So we're going to take a real number minus 0. So throw away 0 under multiplication. So our operation is multiplication here. and we're going to square whatever we get. So is this a homomorphism? Well, yeah, I think it's pretty easy to see that this is a homomorphism if you think about what a square does. So phi of AB would be AB squared, which we know is A squared B squared, which would be phi of A, phi of B. That's not too bad. The kernel of this homomorphism is the set of all real numbers minus 0 such that phi of A equals the identity, and the identity, since it's a multiplicative set, the identity there is 1. So tell me what elements or element is in the kernel here? It's not just 1, because phi of A would be A squared. So I'm looking for all real numbers A such that A squared is 1. Yeah, also -1. So it would consist of 1 and -1. So the kernel here has 2 elements. Now I want to change the problem slightly. It's the same mapping, but now I'm going to change the operation from multiplication to addition. So if I look and I have phi of A plus B, this is A plus B squared, and no matter how hard I try, I cannot make this equal to phi of A plus phi of B unless A and B are both 0. But I'm not restricting myself to just the 0 map. So it's not a homomorphism, no matter how hard we try. And once I decide that it's not a homomorphism, the question of kernel doesn't really matter for us. So as soon as you know that this thing is not a homomorphism, don't even bother with the question of kernel. It's not going to be important for us in this class. All right, let me give you, since this was a multiplicative group here and we haven't done many examples of multiplicative groups, I wanted to give you a multiplicative group homomorphism to think about. So suppose that we are mapping the group of units for the integer n onto the group of units for the integer k. And we're going to do that by taking a number mod n and mapping it to that same number mod k. Remember, this is a group under multiplication. Un is the set of all elements that are less than n and relatively prime to n under multiplication. So what is the kernel of that homomorphism? All right, you got about 30 seconds or so. All right, most of you have answered. This one was a little trickier for y'all, not surprised. The correct answer is C. This is the set of all elements that are relatively prime to n, but are equivalent to 1 mod k. So if you want to think about why the kernel is that answer, The kernel of phi, by definition here, is the set of all x in UN such that phi of x gets sent to 1, because 1 is the identity of u of k. Said another way, this is the set of all x in UN such that x mod k is equal to 1, and that is the definition that we gave in class of this set uk of n. It's this, oh, sorry, y'all weren't seeing my writing. The kernel of phi is defined as the set of all x in the domain that get mapped to the identity element, which is 1 in the range. But our mapping takes the element x and maps it to x mod k. And so x mod k here is equivalent to 1. This is the definition, the set of all elements in UN that are also equivalent to 1 mod k. That's the literal definition we gave of the set uk of n. In fact, this is why this group matters. Remember, this is a group. And that's kind of an important thing that I want to get to here before we run out of time. If you go back and look at all of the kernels that we've seen, this is a group. That technically forms a group, but we don't know that one as well. This one's a group. If we go back to the other examples, we know the cyclic subgroup is a group. We know SL2R is a group. All of our kernels have been groups so far. The set of constant polynomials is a group. You can check that. So we're seeing a pattern here that the kernel of a homomorphism is a group all to its own. And those important groups that we identify going forward are going to be really important to us when they pop up. So I have a couple of properties here that I want to share for elements under homomorphisms. And what I'd love for you to do is take some time over the weekend to compare this list with the same list that we made for isomorphisms. So do a compare and contrast between the two. I want to talk generally about what each of these properties says, and then I'm going to prove property 4 because it's what I just got through alluding to, that the kernel is actually a subgroup of the group G. The first property is the homomorphism will always map identity to identity, right? The importance of that statement is that the kernel of a homomorphism is non-empty, because you'll always have the identity in the kernel. So the kernel is a non-empty subset of G. We're going to prove it's a subgroup here in a little bit. The operation phi G to the n, this is also a very important property because it basically says that phi of any value x is completely determined by what happens to the element 1. Or what happens to the identity, I should say. And the reason for that is I can think of phi of x as being phi of 1 plus 1 plus 1 x times. And then if I use this property, right? So this would be the additive notation, but if I use this property, this would say phi of, so the additive version of this would be phi of ng equals n times phi of g. So a homomorphism is completely determined by where it sends the identity element. And we know it sends the identity element to the identity, but it's completely determined by what it sends phi of 1 to. All right, if the order of an element is finite, then so is its image. And its image will divide the order of the thing that it got sent from. So, you know, if you have an element of order 12, then its image order will divide 12. It'll get sent to an element who has order that divides 12. Now, an isomorphism preserved order, right? That was one of the properties we have for isomorphisms is they preserve order, but property 3 here does not say that this preserves order. It preserves the divisibility of orders, but not the actual order itself. That's one major change from isomorphisms last time. So let's go ahead and prove 4. by property 1, the kernel of phi is non-empty. So let A and B be elements of the kernel. Then what we know is that phi of A and phi of B both map to the identity if they're in the kernel. Consider where phi of AB inverse goes. And at the moment I write that down, you should know what proof technique I'm using. I'm going to use the one-step subgroup test because I'm taking 2 elements from the kernel and I'm showing that AB inverse hopefully is back in the kernel. So phi of AB inverse, because phi is a homomorphism, it preserves order, or it preserves the operation. So this is phi of A, phi of B inverse. But by property 2, phi of B inverse is phi of B quantity inverse. So this would be phi of A, phi of B inverse. Both phi of A and phi of B, by being in the kernel, map to the identity. So phi of A is the identity, and phi of B is the inverse of the identity. But we know the inverse of the identity is the identity, and the identity times the identity is the identity. So AB inverse, that product, gets sent to the identity. So that implies that AB inverse is an element of the kernel, which implies that the kernel is a subgroup of the domain. So we know that whenever we construct a homomorphism, the kernel of that homomorphism is a subgroup that lives inside the domain. And we're going to start looking at factor groups on Monday, and you're going to see why this is going to be a big deal coming up real soon. What I do want to say on 5 is that phi of A and phi of B, in other words, 2 elements get mapped to the same image if and only if their cosets are the same back in G. Because since the kernel is a subgroup, in fact, we're going to prove that it's a normal subgroup here in a little bit, these are actually cosets. So what this means is if the image of a point is the same, then it came from the same coset. That's what that property says. It maps cosets to the same image point. Okay? And then this is a restatement of that, but in reverse. This is actually the more important one to say. This says that the pullback of G inverse, or the pullback of G prime, is G kernel phi. That's kind of the colloquial way of saying it. So if you have an element in the image and you try to pull it back to the domain, the best you can do is pull it back to a coset. You can't pull it back to a single element that mapped to it because there are multiple elements that potentially map to it. I'll draw an image of this for you probably in Monday's class. But understanding 5 and 6 is really important to what we're going to be talking about here in a little bit. All right. Similarly to when we did isomorphisms for the first time, we also have properties of subgroups. So what properties do homomorphisms preserve for subgroups? So it's a whole big list of properties here. And I want us to just talk about them casually rather than memorize each little thing here, just casually talk about what this means. So on 1, it says that the image of a subgroup is a subgroup of the range, meaning that homomorphisms preserve subgroup structures. If you map one subgroup via a homomorphism, it will map to another subgroup. If the subgroup is cyclic, then its mapping is also cyclic. So it preserves, a homomorphism preserves cyclicness. A homomorphism also preserves abelianness. if that's even a word. Now, it also preserves normality, but I want you to understand if I have a normal subgroup of the domain, then I'm mapping it to a normal subgroup, not of the range, but of the image of the domain. So phi of G, if we're not necessarily normal, then the image might not, if we're not onto, excuse me, then the image of our mapping might not be all of the range set. So it'll map a normal subgroup onto a normal subgroup, but it'll do it inside of the image of the mapping, not necessarily, the image is not necessarily normal in the entire group. It's normal in the image. And here's probably the most important one on the list, number 5. If your kernel has n elements that get sent to n elements that get sent to the identity, then the kernel of that will have order n, and it creates an n-to-1 mapping from G onto the image of G. So you actually do get a n-to-1 mapping, which means in particular, if n is 1, if your kernel only has one element, this creates a what kind of mapping? Creates a 1-to-1 mapping if the kernel has only one element in it. We know every kernel has the identity in it, so that one element must be the identity. So if you take 5 and pair it with 8, these are two of the most important properties here, 5 and 8. It tells you that if your kernel has only the identity element, then the homomorphism is actually an isomorphism. So if you create a mapping from one group into another, and that mapping's kernel is only the trivial element, then the mapping must have been an isomorphism. Now you have to have that the homomorphism is onto, right? So you still need onto, but property 5 gives us 1-to-1. So if you have a trivial identity and your mapping is onto, then you know you have an isomorphism. So checking how many elements are in the kernel is a way for us to bypass, if you will, to having to check 1-to-1. You can simply check that you have a trivial kernel, and that's equivalent to saying that a homomorphism is 1-to-1. Property 6 is a restatement of the element property from over here. We know that the image of an element divides the order of the element. Here, we know the image of a subgroup divides the order of the subgroup. So the image of a subgroup divides the order of the subgroup. And then 7 is the inverse version of 4. So it just says that we preserve normality in both directions. So what I want you to do, like I said, is go back and compare these to the list that we had for isomorphism and see what things are left out. Now, that's all the time that we have for today. What we're going to get into on Monday are applications of these ideas, right? So you really want to concentrate on the properties here that we've laid out. And then I'm going to, in Monday's class, start applying homomorphisms to a lot of problems and show that it gives us a lot of information about the groups that we're targeting with these mappings. All right. I hope you all have a great weekend. If you run into any questions and need me, just holler. See y'all back face-to-face on Monday.
Have a nice weekend, Dr. Arkey.
You too.
Have a good one.
You too.